Hey guys, I'm back. This time, I think what I'm going to do is step through the backpropagation algorithm for a very, very simple case, and we'll sort of plot out just a simple, you can see here in a diagram, I have a simple single neuron with a single weight, no bias, no nothing, and we'll step through it and see how the algorithm functions and how it converges to a data point. All right? So this is sort of the standard example. This is straightforward. We have our, whoops, let me see if I can make this bigger. We have our transfer function sigma, which is just the regular 1 over 1 plus e to the negative x. Recall that the derivative of that is just sigma times 1 minus sigma. Also recall the error function that we have. It's given by, right, this error is 1/2 the sum across all the data points of the difference between the output and the target value quantity squared. And if you want to look more into this derivation, you can look at my other video. But, so as a simple example, let's just take a single neuron with only one incoming weight and no bias. So here's this picture, right? I have some input value x. I have a weight w that connects that input to the node, the neuron we're looking at, which has a transfer function sigma. When you evaluate that, you get output script O. Okay? The equation which defines this is very, very simple. Script O equals sigma of Wx, right? The weight times the input. So now, using this error function up here, I'm going to compute the derivative of error with respect to the weight. So essentially, I'm just doing derivative of... Now, also, there's only one data point in this example, so the sum goes away. This is 1/2 output minus target value squared. When you take that derivative, you get output minus target times output times 1 minus output times the input value, right? And this is fully worked out in the other video, so that's less important. I mostly want to just have this. This is the sort of all spelled out version in terms of our target value t, our weight w, and whatever the input value is x, all right? And it is this expression right here. So now what I'm going to do is pull up a win plot, and we're just going to, in fact, I'm going to build it with you step by step. Close that so that you can follow along if you want. Win plot is a really awesome little plotting program that is totally free, and I highly recommend you go grab it. Well, you're going to have it if you're going to follow along. Otherwise, enjoy the ride. Let me pause this and sort of reorient the screen. All right, so I've pulled up just a single window here. This is a 2D plotting window. So the first thing I'm going to do is define a user function. I'll just call it SGM, and it's going to be the sigmoid 1 over 1 plus exp of negative x. Enter. Now this is just for convenience. I just want to refer to this function. So for example, I could just go explicit plot sigmoid of x. And there it is. This is my little inventory over here. And so there it is, right? This is the standard input. The standard transfer function. So let me delete that. One of the cool things we can do in here is we can create some parameters. So let's create parameters A and B. A, individual parameter B, B. And this is actually going to be the XY pair that I'm going to train this neuron to find. Okay, so let's go into equation and plot a point, and it's going to be point AB. It's going to be solid, size 2. Blue is fine. Okay, all right. So I can grab these scroll bars and move this dot around. Right. So let's make it like 2. I don't know. 0.65. Okay, just made that up. Now let me set some bounds on this here. So let me change the view. This is going to go, let's say -5 to 5 is fine. -0.1 to 1.1. That'll be good. Okay. Right. So here's my data point. I can drag this guy around. So 2.65. That sounds good. Now let's create. Let's grab another individual one called W, and this will be the weight, the one weight that we have. So let's just set it to, I don't know, 1 for now. And let's add an explicit one, which is the sigmoid of w times x. All right. Now this is the sigmoid function. I can change how steep it is by changing this weight w. All right. And you can see it changing here. Let's go like 2, set that as the right bound. -2, set that as the left bound. Right, you can, wow, that's going really fast. You can do all sorts of nice stuff where it'll automatically animate it for you. But that's besides the point, right? Anyway, okay. So let's just set it to 1 for now. So this is the regular sigmoid. Okay, now so what I want to do is recall this beast here, this expression. So what I want to do is take this sigma of wx minus t times sigma of wx, 1 minus sigma of wx times x. This is the derivative of the error with respect to the weight. Now if you recall from the backpropagation algorithm, I'm going to move opposite this direction. So I want to display this somehow. Okay, so I'm going to keep that on tap. Actually, you won't be able to see it, but I'm going to put it off to the side, just so I have the equation sitting here. Okay, now, what I'm going to do is let's go ahead and create a segment, xy, and it's going to go from, let's say, -2, I'm sorry, -3, 1/2, to -3, 1/2, minus, and this minus sign here is going to be because I want to move opposite to this direction, and then I'm just going to plug in this formula where w is our weight w, t is this target value that I want to go through, 0.65, etc. Okay, so I'm just going to plug that in right now. So this is sigma of w times x minus the target value, which is b. Oh, I'm sorry. For x, I'm actually going to put in a, right? A is the input value that corresponds to the output value of 0.65, and I want to evaluate the derivative at that point. So for x, I'm plugging in a, and for t, which is the target output, I'm plugging in b. So that's what's going on there. So times sigma of w times x times 1 minus sigma of w times x times x. And let's make this an arrow that points to P2. Color black is fine. Okay. Oh, I'm sorry. I think I did that sideways. 0.5. Oh, that's what I did. -3. Okay. Let's see what happens here. Oh, see, I screwed it up. X is a. W times a times a. Let's try that. Okay, so now we have a little arrow. And you can see as I change the desired data point, it moves up and down. And essentially, whichever direction this thing points is the direction that I'm going to have to change the weight in. Okay, so let me bound this between 0 and 1 to the right. And what do we have? I don't know, 0.65, I think that's what it was. And 2. Okay. So, let me go ahead and make a little text box over here. This is the delta in W, right? So whatever this arrow says to do, I'm going to take my current value of W and move it down or up, depending on what it says. Okay. So this is my data point in summary, right? The point 2, 0.65. I want this curve to go through that line. What I plugged in over here is just all I did really is I built an arrow that points in the direction that I want to change w, and that's literally just the derivative, right? That's from our calculus we did earlier. So, well, what does it say to do? Right now it says it needs to decrease. Currently it's 1, and you can see it's too high. So let's start making it smaller. Okay, now it's 0.96. It still says negative. So let's keep making it smaller. I'm down to 0.8, 0.75, 0.68. And you can see, I mean, the curve is changing everywhere, but this distance right here between the data point that we want and the data point that the node is outputting is decreasing. And all I'm doing is whatever this tells me. So I'm going to keep decreasing it. Now notice that the arrow still says it's decreasing, but it's shorter because the derivative is, well, it's shallower. If you were to plot it, it's not quite as steep because I'm getting closer to the actual solution. So I'm just going to keep doing that until the arrow goes away, right? That looks pretty good. I don't really see the arrow here. I'm basically there. Although the V still says it's pointing down, so if I go down again, oh, I went too far. Go back up. Let's see, I don't know, 0.3, 0.35, that's too much, 3.2, that's too much, 3.1, still too much, 3.05, okay, 3.05, 3.06, I mean, this is really pointless, I'm pretty darn close. Anyway, so you can see the derivative is very, very small. I've sort of adjusted w to come close to this point, and the derivative here is basically 0. I mean, the line doesn't even plot, and you can see, ta-da, I found it across the line. So that was a very, very long worked out example. So now let's pick another point. Let's say I want it to go through, actually let's leave it over here. Let's make it 1 and then 0.2, something like that. Okay, so it's saying the weight has to go down quite a bit. So let's keep moving the weight down, 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 down. And you can see I'm already into the negative range. The weight is negative 0.2. Let's keep making it negative, negative, negative. Now keep in mind, I'm just watching what this delta is telling me. Negative, negative, negative. So I can keep going until the arrow flips right there. And ta-da, there it is. It goes through the point. The derivative has gone to 0, and that's it. All right. So that's it. This is kind of a fun thing. You can kind of pick. Let's say I wanted to go through, I don't know, 3 and 0.25. Then I need to move this up. And so I'll keep moving it up. And see, now this is interesting. You can see how the derivative grows. Even though I was farther away over here, and it's because the sigmoid gets so flat, then you kind of hit these plateaus out here where the derivative isn't very large. And so it can be slow going in the beginning, and you can see as I get somewhere in this range, the derivative actually gets larger in the same direction, and I start to converge quickly. And then as I get closer and closer, it slows down. Oh, and I pass it. I don't know, negative 0.38. That's too much. Anyway, so there you go. It goes through the point. In the next one, the next video, I'm going to throw in a bias term in here, right? It's going to work out exactly the same way, except this will be 1. This is probably kind of small. So I'll throw a bias in here, and we'll work out the next line, and we'll add it in as another parameter box right here, and we will pick a point and adjust both of them, and we'll see how that goes. Okay? So I will see you guys in a second.